Good afternoon, teacher.
Very few. I'm wondering, I think people are still switching, but let us have a prayer, opening prayer. Who is ready to pray for us? Aha, banange. Now let me do kanem kanabidi kakumba mwanyi. Akampurira.
Yes, teacher.
Please lead us in a prayer.
Let us humble ourselves and pray. Oh Lord, we thank you for this day. We thank you for the gift of life. Lord, as you're going into this physics lesson, let us understand this, the teachers and other people who have attended this lesson. Let us remember whatever have been taught, and Lord, we pray that we may always remember this, oh Lord, and we pray we're going not get any disturbance of the internet or anything that will distract us. In Jesus' name I pray. Amen.
Amen.
Okay, as we wait for our colleagues to join us, because I believe more and more are joining, we can do a small recap. We have looked at 3 terms. 3, are they 3? Yes, 3 basic terms, I think. We have looked at the mechanical advantage. Joan Natkunda, what is mechanical advantage? Joan Natkunda, what is the mechanical advantage? Okay, Joan doesn't remember. Yes.
Mechanical advantage is the ratio of load to effort.
Load to the effort. Now, I tried to tell you the other day that mechanical advantage should be 1 or greater than 1. Can anybody tell us the reason why mechanical advantage should be 1 or greater than 1 for a good machine? Daphne?
Teacher, because for a good machine, let me say, you're supposed to use less effort. Because if you use more effort than the load, that won't be
You are not
to your
simplifying
advantage.
work. Is that okay?
Yes.
So if you use more effort than the load, for example, I get 10 elephants to pull a small ant, that is wastage of resources, isn't it?
Yes.
Okay, so we are supposed to use a smaller effort to overcome a larger load. That's why mechanical advantage should at least be equal to 1 or greater than. Most effectively, the larger the mechanical advantage, the more efficient our machine is likely to be. I'll talk about that word efficiency later, but simplifies work. Okay. There is only one machine which has that exception. Can we remember which machine that is?
Screws.
Zora, which machine is that?
Screws.
The screw. And why is the mechanical advantage of a screw less than 1?
Teacher, me.
Zora.
Because it's not, okay, I don't remember properly, but I think it's not supposed to move when it's put inside when it's joining the 2 parts together.
Okay, when it's joining the 2 parts together, it is not supposed to move. So who can remember the reason why does the screw have a mechanical advantage less than 1? I'm asking Joy, Angel. Joy, Angel. Joy Angel. How many are you Joy Angels? We have very many angels. Okay, everybody's an angel. I'm jumping from Joy. I'm going to Johanna Ayuki.
Yes, teacher. What I remember was it's because of the friction, and you have to overcome that friction, which is inevitable. So that's why.
Yeah, the screw has a lot of friction. Is that okay? That friction is necessary because it is actually the one that does the work for the screw to keep the two bodies together. The two bodies it is joining must keep them together and they not always be moving. So that friction is very, very important to oppose any motion in the joint or the plates that the screw is joining. So the screw always has a mechanical advantage that is less than 1. That is basically what we talked about. We also talked about another term which we called velocity ratio. Who can tell us what velocity ratio was? The numbers are gathering, so that is okay. Amelia, who is this Amelia? The name is running. Amelia, what is velocity ratio? When I use the name Amelia, I think I'm not defining anyone. How many Amelias do we have?
Why?
Hey, Amelia, that one. Amelia, what is velocity ratio?
Teacher, are you saying me?
How many Amelias do I have? I have one only. Now she's asking me another question. Amelia, you are the only one.
Teacher, I don't remember.
Amelia Nadunga, yes, this one. You don't remember velocity ratio?
Remember.
Amelia, look at your notes. Do you have your notes?
Yes, teacher.
Yes, what is velocity ratio? Okay, Amelia doesn't remember. Abigail Sima, what is velocity ratio? Abigail, it is not because you are putting up your arm that I'm going to choose you. I'm also roll calling. I'm trying to see whether people who are attentive and those who are not attentive. Abigail, Sima, whenever you cannot answer, it implies that you are not attentive. These questions that are online are very funny. You are the only, your own disciplinarian. You're the person who is in charge of your own learning. Is that okay? So as we are learning and you're not in charge, definitely you're not going to remember. Yet we are very direct. So Nadunga doesn't remember, Sima doesn't remember. Okay, Adele.
So the velocity ratio is the ratio of distance moved by the effort to the distance moved by the load in the same time.
Who's talking? Who is answering me? I can't see you. That's the same people who are always in class are the ones answering. Okay, velocity ratio is the distance moved by the effort to the distance moved by the load. Paula, thank you so much. By the way, I wish I had prizes issue. If I was Inganze Uvanzani Kali, I would have given you this heaven. Okay, because there are really some very serious people. Okay, we talked about that velocity ratio, and please I emphasize that remember velocity ratio as the ratio of the distance moved by the effort to the distance moved by the load. I told you forget about the velocity of the whatever, that other definition. Okay, now we were moving to another term, very, very important term, and this term was called efficiency of a machine. Machines are supposed to be efficient. So let me share the notes and you read for me the efficiency of a machine. Let me see, efficiency of a machine. We talked about it, but briefly. Very precious. I'm giving you opportunity to talk to us, read efficiency. Precious.
Yes.
Read for us efficiency. The notes are already displayed.
Efficiency. This is the ratio of work output to the work input expressed as a percentage.
Okay, and then
Efficiency is equal to work output over work input times 100%.
mhm.
The ratio of mechanical advantage to velocity ratio also gives efficiency, but it is not used as a definition for efficiency.
Okay,
Efficiency
so that we can stop there. Is that okay? We can stop there. That is not very, very important. We are trying to carry through what is important and what is not important. So let us look at what affects efficiency of a machine. I hope when I talk about efficiency, you can tell me, what exactly do I mean? If I tell you that you are a very efficient person, what do I mean? Can somebody first give me that definition? What they understand by somebody being efficient? Okay. Nakabona Lindsay, can you tell me what we mean?
Helpful, a person who is efficient, hardworking or helpful. That's what
That
I
person
think.
is hardworking. Okay. That is her understanding of hardworking. Now, Lauren Lusiga, what do you understand by a person being efficient?
Efficiency, like a person being efficient, I think someone who does their work to the fullest, like does it properly.
Does it properly. Okay.
Yeah, properly.
Very good. I think you are almost there. Akelo Damali, Daniela, what do you think an efficiency is all about?
I think efficiency refers to the level of performance that someone uses, like how much they put in and they get more from, like they get more results.
Exactly. I think she has given us a proper definition. Efficiency means that whatever you put in is almost equal to what you get out or more. Are we together? So you have as little circumstances, if we can measure what we have put in to what we have put out, and we have wasted as little as possible, we are likely to be more efficient. Is that okay? When I put it in terms of hard work, sometimes we have this saying that hard work pays, but please let us convert it to a better your level. These days, I would rather say that smart work pays. Is that okay? We may say hard work pays, it is okay, but smart work pays, because smart work is likely to be more efficient. Because in most cases, what we're trying to do is what of our output compared to what we put in. If we find that we have put maybe 100 and what we get out is just 50% of our input, then we are not being efficient. So the best way, put in 100, at least get out 80%. The more you get out of what you put in, then you are very efficient. Is that okay, people?
Yes, teacher.
Yes,
So
teacher.
when we talk about something being efficient, it means it minimizes wastages. The wastages are very, very minimal. It only has to spend, for example, if I talk about an efficient car, it is a car that consumes as little fuel as possible. So it gets the maximum out of that little fuel that it has put in. Is that okay? Then that is an efficient car. But a tractor, for example, if you put in all of the energy is wasted in driving the tractor instead of digging, you can imagine. Do you get that idea?
Yeah.
Yes.
So efficiency basically means that if you have put in, get as maximum as possible out of your input. So that implies it's going to be measured as in percentages, because are the best representations. If I put in, for example, 50 and I get 45, that is a very good efficiency. If I put in 50 but I get 20, then I'm below what the required levels. So that's basically what the meaning. Okay, now we have used those terms. I hope we have understood what efficiency is all about. So we look at the factors that affect our efficiency.
Excuse me,
In our
teacher.
machine, there are basically two. Yes, please.
Teacher, I beg your pardon. You should put in more and get less, or you put in less and get more.
No, you put in more, and if you put whatever you have put in, by the way, it is whatever you have put in, get as much output as possible, then you are efficient. But if you have put in a lot and you get so little, for example, if you are let's look at seeds. You know, we plant seeds of maize, isn't it? By the way, do you plant? Okay.
Yes.
If you do planting of seeds,
Yeah.
I may get 3 or 4 seeds of maize altogether, and I start planting. But the maize cobs that I get, does that give me only 1 seed because I planted 1 seed?
No, teacher. No.
The fruits are very good examples that you plant 1 seed, but they give you cobs of maize, moreover, more than 1. Isn't it?
Yes, teacher.
So all these variations, plant 1 seed, get 30 cobs of maize. That's basically what I'm talking about. But suppose you planted 1 seed and it gave you 1 seed, you would even quarrel. You say, what kind of maize is this? Isn't it?
Yes. Yes.
So that's why God cast that tree, which you had no fruits. Am I making sense? So when you put in something, the output you get out, that implies that it is efficient. But so that's basically the measure. If I am, you get my point.
Yes, teacher.
Okay. So there are factors, when we go back to our machines, we talk about factors that affected this efficiency. What are they? You can read for us. I'm picking Nakabuye. I've seen a Nakabuye here. She has disappeared again.
Sure.
Anybody called Nakabuye? Can Nakabuye tell us quickly?
Yay, ma'am.
Nakabuye has disappeared. Okay. Mercy Top is, hey, you are there. Kale, quick.
Pardon, teacher?
Nakabuye told him class. Jacinta, I want people who are listening to me. I don't want people who are not listening to me. Jacinta, are you listening? Can you read for me the factors that affect efficiency?
Factors that affect efficiency of machines. A machine that is 100% efficient is called an ideal machine. Machines are never 100% efficient because of the following factors: friction in the movable parts of the machine, lifting useless loads which are part of the machine, improving efficiency of a machine.
First hold on. Let us look at that factors and understand them. Remember, this is not about all like you are just reading. No, you want to understand friction in the movable parts of the machine. The other time we discussed a car. I hope you remember. Do you remember that discussion? So we said that a car is a complex machine and it is full of moving parts. Can you give me some of the moving parts?
The tires.
Steering wheel.
The steering wheel.
The gear shaft.
The gears.
The
Very
engine.
good. Okay, the engine is a little bit complex, but it's not okay. The engine, basically the pistons, they are also in moving. So how is the friction in the car reduced?
By lubricating.
There is a lot of lubrication. Is that okay? So whenever you hear mom, dad saying that I'm taking the car for servicing, one of the things that they are going to be doing is to make sure that they reduce friction that takes place within the car, the moving parts, even the doors, by the way, the hinges, they are lubricated. If you look at them carefully, you realize that, especially for the rough cars, you even see the grease hanging out. But for most of these modern cars, you rarely see those things. They are hidden because they made that new. But that is, I think, a very good example where friction is always reduced by lubrication. Do we get rid of it completely?
No.
No. Is that okay? It is very difficult to get rid. So we just reduce it, but we don't get rid of it completely. I hope you get the point.
Yes.
Okay. So whether we like it or not, there will still be that little friction that will reduce the efficiency of the car.
Yeah.
Okay. Irrespective of lubrication. Now, number two, there is lifting useless loads. I think I wanted to use the example of the car. What is the useless? What are some of the useless loads? What are you carrying? What is your major purpose? What are you doing when you move in a car?
You're supposed to go to a place.
Or you are supposed to carry
Transport.
something to a place, isn't it?
Yes.
Yes.
But in the process of carrying that item to that place, what do you bring along?
The car.
The car. You get the point. So that is what happens. Part of the car has to move with you. And in most machines, that's what happens. You always come with that unnecessary avoidable evil with that. So that's what we call lifting the useless parts of the machine. What do we do if we want to reduce this load as we carry along the car? I mean the machine. What do we do? Look at how what we do. Anybody
Making
who can
it
tell
using
me
light
want
parts.
to reduce that?
Making it using light parts.
Light parts. Can you, when we talk about that light, what are we talking about? Are we talking about solar energy, light, or what? What are we talking about? Can you break it down? We are using light parts. What do you really mean?
Like something
But
that
not
isn't
very
heavy.
heavy.
We are
Light
using
opposite of
materials that don't have a lot of weight. Is that clear?
Yes.
So, if you look at, I always want to talk about cars because Uganda has very many samples of cars. Who can think about the most modern car? Give us an example.
Range.
What?
Range Rover.
Okay, a
Range
Range
Rover.
Rover. Now, who can give us a relatively very ancient car?
Corona.
Now,
Vintage.
what have you observed about their body work,
These
their materials, the materials that make their body parts?
They are
They're
very
heavy.
They are very small.
Which materials are
All
heavy?
are very light.
They are
Which materials?
thin.
Yeah?
They are
Really small.
thin.
A lot of noise.
Yes, they make a lot of
Organs
noise.
overshape.
They overshape.
They are
Okay.
thin.
Okay. But one of the things that you're going to observe about the more recent, the more modern cars, they use very light alloys. They try to move away from iron, those metallic kind of substances, and they're actually using alloys. These days, they're talking about a lot of carbon fiber. There's that material referred to as carbon fiber. Those who do a lot of Googling, go and look at carbon fiber. You are realizing it is quite very strong, but a very light material, and it is right now being used a lot as far as cars are concerned. The other thing that I can give you is just look at the bumper of an ancient car and the bumper of a modern car. You really realize the difference. The bumpers of old cars are made out of iron, but these ones, even a kid can kick it. Do you realize that? The bumper of a modern car, even a kid. For example, if you look at a Wish, those who have those cars called Wish, you can kick that bumper. You may be passing Madame Juliet's car by accident, and then you kick that bumper, and then you get frightened. But it will come back. Is that okay? But the purpose is basically to make the car as light as possible. There is a question?
Yes, actually, if you use aluminum, is that light enough?
When you use what?
Aluminum.
Aluminium. Okay, I think, yeah, it is. I'm not come with the names of those real alloys, but what I'm trying to say is that these days they are using a lot of light materials. We can look them up, we can search them up, but that's the basic point. Is that okay?
Yes, thank
Yes.
you.
Okay, so factors that affect efficiency are friction and lifting useless loads. What do? We lubricate as much as possible. We use very light parts. There is a third point I want to add to this improving efficiency of a machine. Let me see whether I can type it here. Okay. Let me type that point and you capture it at this point. By increasing the load or mechanical advantage to optimum
Where the fuck is the laptop charge?
Let me just leave to that. When I talk about by to optimum, you may not understand. Now, if you want to increase the efficiency of a machine, please make it carry the required load, or let it have the required mechanical advantage. For example, let me just try to say this. Most of us have a tendency of moving in a car alone, yet the car is supposed to carry how many people?
5.
Maybe 5. Is that okay? Now, this is what I'm trying to say. Suppose all of you 5 people in the family went to a function, each one in his or her own car. You understand what I mean?
Yes, teacher.
Yes, teacher.
Are you being cost effective?
No.
So how can you become efficient?
You all of you using one car.
You can use one car. You understand? So that you don't put in a lot, but for so little. So we are going to realize that the efficiency of a machine can be increased by increasing the load or the mechanical advantage. So try to choose the machine for what it is meant to carry, rather than killing a mosquito with a gun. That is the analogy. I think I'm using a lot of analogy so that you understand me. I don't want you to start writing killing a mosquito with a gun. I hope you get my point. How would you kill a mosquito?
Use your hand.
You hit it with a
But
wall.
suppose you got a gun. What are you being efficient?
No, you're wasting your
So
bullet.
certain loads, if a machine is meant to carry 3 kilograms, make sure it carries 3 kilograms. Don't overload it altogether, but don't also make it carry something that when it can carry more. You understand? That becomes a wastage of energy and effort. Am I making sense?
Yes, teacher.
Okay. There are 3 ways we can improve the efficiency of the machine. Number 1, we lubricate. Number 2, we make it out of very light parts so that they are not very heavy. Number 3, we make it carry the load it is supposed to carry, rather than carrying less loads. I've given you an example of a car. If mom, dad, everybody, even the baby went in his or her own car, that's wastage of resources. Clear?
Yes, teacher.
Okay, so I hope we have understood that. Now we are looking at the types of machines. These are simple machines. We are using the word simple because what we are going to discover that the machines we talk about are a combination of all these. Is that okay? No single big engine or complex engine. Every complex engine has one of these. These, when we refer to as them being simple, we are calling them the fundamental machines from which others are derived. Are we together?
Yes.
Okay. So what do they include? You gave them to me the other time you made the list. They are called read. Okay, I'm not Ndagile. Ndagile, your arm is up.
Okay. Types of simple machines. These include levers, pulleys, inclined planes, wedges, screws, wheels, and gears.
Ndagile, your network is always clear. What is happening today? Huh?
Sorry.
Read those things. I've not heard anything.
Can you hear me now? Teacher, can you hear me now?
Yes, I can.
Okay. These include levers, pulleys, inclined planes, wedges, screws, wheels and axles, and gears.
Thank you very much. Misspelling, I'm correcting a mistake here. Wages, we are not talking about salary. Is that okay? We are talking about a wage. Who knows what a wage is? That is the only machine which is a little bit rare. Anybody who knows what a wage is?
It's a cutting tool.
It is a what? Who is answering me? A cutting tool. Is that what I heard? The answer, Julie.
Yes, teacher.
Oh, you don't know what wages are.
Teacher, is it like
Give you an example of the wage.
Teacher, is it like
It's
a
supposed to
triangle?
prevent movement. For example, if I want, you have a car on an inclined plane, and you fear that if you leave it there, it may move. You get a kind of a stone and you put it below the car tire. That is a wedge. Is that okay?
Inclined planes connect.
If you have a door that is always not closing properly, you get a piece of paper, fold it, and you put it between the door and the whatever. That is an example of a wedge. Do you understand now what wedges are?
Yes.
Wedges are supposed to hold firm. They are supposed to hold deep certain items that are movable. Usually you want to hold it in one place. So what you do is you wedge it. Is that okay? By putting something that prevents it to move. So wedges are examples of that. Usually they are triangular in nature. Most wedges are triangular and you place it below. So for example, the wheel of a car, if you see, so that it doesn't prevent that movement. The head of an axe is an example of a wedge. Is that okay? Okay, so don't discuss wedges so much as they are machines. They also use a lot of friction, but let us look at the first common machine that we know. These ones, you know, all of you, most of them from your primary, because you did PLE. Anybody who did PLE?
Yes, teacher.
Yes, teacher.
Yeah. Oh. I thought there was somebody who did not do PLE, because there are people who did not do PLE. They start from Kenya. You don't have any certificates from Kenya.
Which I didn't do.
Who you didn't do PLE?
Certified
Who are
farmer.
you? Who are you? Sanyu. Sanyu didn't do PLE, so she should not be part of this class. Okay, PLE, levers. Give me the levers. There was a girl called Lisa. I think she wanted to say something. I ignored her for a long time. She also gave up on me. Lisa, please, I remember.
Lisa.
Yes. Lisa, carry us through the rivers at least.
Who?
Lisa,
Teacher,
wow.
I'm Shona Lisa. So I read.
Read.
Okay.
Not one.
Levers. A lever is a simple machine which has a turning point called fulcrum or pivot. There are three classes of levers, namely first class levers, second class levers, and third class levers. notes. They may be recalled using the synonym PLE.
So PLE, who remembers what PLE stands for? Why do we select PLE?
Pivot, load, pivot.
No, why do we select PLE? It is selected by on a specific purpose. Why PLE?
According to the class of levers.
P stands for pivot, load, and effort.
The middle.
Let me select only this. Tina.
Teacher, it's because PLE stands for the middle part of the machine. That for first class levers, the pivot is in the middle, then second class levers, the load is in the middle, then third class levers, the effort is in the middle.
Very good. So I'm not going to be wasting a lot of time with the levers because we know all of them. So levers are named according whatever is in the middle. You just look at what is in the middle. If it is the pivot, then that is the first class. If it is the load, that is second class. If it is the effort, that is third class. That is, I hope, very good. So the first class levers, give us the lists. I was Tina Nabufu. Tina. Tina, carry us through those first class levers quickly.
These are levers that have the pivot between the effort and the load. Examples of first class levers: the children's seesaw, pair of scissors, the crowbar, the beam balance, pair of pliers, garden shears, spade, claw hammer.
So for me, when they talk about first class levers, I remember the children's garden. Because the children's garden, what do you find there? A seesaw. What else?
Spade. A pair of scissors.
A pair of scissors in a children's garden. You want to kill children?
Spade.
Garden shears. What are the children doing spades with? You tell me exactly. A spade. What are they used for?
Seedlings, but no other children's
For us, we used to play with sand. Don't you go to the children's garden and you play with sand? A crowbar. What do you use a crowbar for?
To lift.
I told you, I remember some of these machines from the children's garden. Let me tell you what the machine which I remember. Do you slide in a children's garden?
Yes.
Yes. This is that machine where you are sliding from the top to the bottom. No, it is an inclined plane.
Inclined plane.
You remember the inclined plane? We are going to talk about the inclined plane. Yes? Then there is the seesaw. Then we play with a lot of sand and so on and so forth. But there are so many things that you can remember from the children's garden. So that's why I told you, okay, then there is the garden. We talk about the clothes. Most of these things are garden tools. There is the garden shears, there is the spade, there is the crowbar, etc., etc. Is that okay?
Yes,
okay.
teacher.
What else do we do with the beam balance? Beam balance, what do you measure?
Wait.
Measure weight using a beam balance.
Sugar.
Wait.
Mass.
Mass is the one that you measure using a beam balance. Is that okay? Okay, girls, those are the different tools drawn there, and all of them are trying to show you where the pivot is placed. Is that okay? As long as the pivot is in the middle.
The spade doesn't have a pivot in the middle.
The spade. Why was it included here?
The spade, it doesn't have a pivot between the load
I
and
think
the
the
pivot.
spade should be removed. It is not a first class lever, really. Let me see. No, it depends on how you use it. Yeah? It shouldn't be first class lever. So let us remove, I don't know how many. This is not, spade is not. Remove the spade. What have I done? Let us remove the spade. The spade was the diagram. It is the whatever third class lever. Please remove the spade. I'm trying to remove the spade from the first class levers. What else should be removed? Let me see. The garden shears is, the crowbar is, the scissor is, the scissors, scissors also, yeah, they are. So it is only the all these, yeah, the ones that are remaining are first class levers. So second class lever, I think this one was supposed to land here. The spade is in third class. I don't know why it was brought here. Yet it looks like a good diagram. Okay, these people, we shall remove that and put it where it belongs. Okay, now can we discuss the second class levers also?
Yes.
Yes, tell us the second class levers. I'm trying to place the spade somewhere where it belongs. Okay, let's go back to the second class levers. Who is reading? There is somebody. Paula, I think if I ignore you, I'll be killed. So Paula, I cannot afford to ignore you. Paula?
Yes, sir.
Second class levers.
Oh, second class levers. This lever has a load between the pivot and the effort. Example, a wheelbarrow, a nutcracker, a bottle opener, a stapler, a nutcracker, and nail clippers.
You know nail clippers. I hope you cut your nails regularly. These days we are getting at, you don't. I knew you had grown up.
Protection.
You girls, you are growing
They
up.
just break
You
off.
cut your nails, you are still at school. Okay?
Yes, teacher. We
Are 2 years
Yes.
at home.
So those
Teacher, they
are
naturally follow.
Yeah, you're not what?
They naturally follow.
Okay, come back. Okay.
We
Those are
give
second
them
class.
protection.
Those are the second class liver. Let us move to the third class quickly. I'm choosing Topista Mercy.
Third class lever. This is a lever where the effort is between the pivot and load. Examples of third class levers: pair of tongs, forceps, the force arm, shovels, fishing rods.
Shovels, these shovels actually are the spades.
Fishing rods, human forearms, legs, tweezers.
Now these things of legs and forearms are not necessarily machines, people. Is that okay?
But they simplify work.
Yes, they no. Machines, did you create your forearm?
Not it.
No.
So these forearms and legs, listen very carefully before we put them in machines. We should think about them carefully. They work like altogether. They have that capacity to work like, but they are not machines. These things don't simplify work. They're already naturally occurring. You understand? Because so that was an application, but they are not machines, people. Altogether. Otherwise, I'm going to call you a machine. Machine Jovia, how are you?
Yeah.
That's okay. That's not normal. So let us not, they apply the principles, but they are not machines. So I want you to pick those things, get them out pick the man-made items and refer to them as machines altogether. Because
Teacher.
it will depend on how I use my leg. A leg can fall in any form of a machine, by the way. It depends on where I apply the effort. Okay, so I'm removing them. Okay, even the human arm, they are not machines because it depends on where I want. At quarter one, it is not a second arm lever. Yeah, it appears twice. Thank you.
What about a robotic arm and a robotic leg?
Now we are talking about robots. Those are machines, man-made. Is that okay?
Yes.
But now you want me to call you a robot?
Sure, no, but some people have them.
Yes, they are machines, but they are not. Yeah, we understand they apply the
Talk
principle.
about those muscular people
My dear.
who have those biceps.
Okay, let's leave that argument for another day. Let us move on. Okay, now the velocity ratio of a lever. How do we find the velocity ratio of a lever? It has the same definition. I'm not going to waste a lot of time about it, but let us look at the efficiency of a lever. How do we make the lever as efficient as possible? Read.
The efficiency of a lever is improved by increasing the distance of the effort from the pivot or turning point.
Okay, now I'm going to talk about this efficiency practically. Are we together?
Yes.
Are you listening? Now,
Yes.
levers in most cases, if you have observed, they have a pivot, they have a turning point. Is that okay?
Yes.
Now,
Yes.
the best way to increase the efficiency of any lever is to place the effort as far as away from the pivot as possible. You place the effort as far away from the pivot as possible. You increase the distance of the effort from the pivot. How do we handle this? Look at the door handles. All of you have doors in your vicinity, your neighborhood. Where is the door handle located in reference to the pivot or to the hinges?
At the extreme end.
Yes. So we observe that the handle is at the extreme end, as far as away possible from the pivot or the hinges, isn't it?
Yes.
What about the window, the handles of the window?
The same thing.
Same thing. Is that okay? It is the same thing. Now, I've talked about the playground because I told you that playground is a very good place for us to exercise. Have you ever had a game with your mom on a seesaw?
What?
Yes.
No. With your mom.
They're asking me what?
When
You have never played with your mom?
No.
Teacher, honestly.
They're always
On a seesaw.
2 years ago.
Which nursery schools did you
No.
go to?
Teacher, she wants to be
Teacher, not on a seesaw.
Teacher,
Not on a seesaw.
Okay.
Okay. Have you ever had tug of war
Hi,
with her?
Sarah.
No.
Yes.
Hi.
Teacher, who does that?
Hey, the teacher.
That's that. So your mom are becoming aliens to you. Okay, what about your dad?
No.
Yes, of course he knows.
Right.
Asking somebody who has ever had a game on a seesaw and she has sat on a seesaw
On
with
a
a
swing.
pedal. On a swing.
Me upset.
So we have ever sat on
Yeah.
a swing.
What happened?
With
Suppose
some
you
of the
want to lift your
children.
mom. What has happened? Because I believe that you are
Me
lighter
and
than
Shona.
them.
Teacher, you can't.
Remained
What?
up and
How
they
do you play
remained
with
down.
them on a
She
seesaw?
stays down.
If you're very fat, you sit
You have to
near
add
the
more weight
pivot.
to your
That she
side.
went up.
You have to add more weight. But how do you add more weight to yourself? When
No,
you are,
you sit
what do you
further
do?
and
Sit with someone else.
from where she's
You
sitting.
sit with
And then
somebody else. So you gather the whole family. The whole siblings and they sit on one side.
So the heavier person
Chaining
sits
the one
further,
person.
closer to the pivot, and then the lighter person.
But the best thing you can do is to make sure that you are as far away from the pivot, and your mom sits closer to the pivot because she is considered to be heavier. Is that okay?
Yes, teacher.
Yes.
Okay. Bana tebasanya na bamama baabwe. Bamama bwe muba muli eyo musanye n'abaana.
Daniela, you have
Hi, Sarah.
Excuse me, teacher, I have a question.
You see what teacher Jam is trying to do for you?
Yes, sir.
Your moms are too serious. You people. For us, we used to play with mommy and that, and that builds relationship.
They used to play, but not
All
when
you know is to go to Java.
She'll beat us when we win.
That was then.
I have a question.
Here, you people, you are quarreling. I see people in children's gardens every day. Eh? Then you see the other one is seated the other side, then the other one is seated the other side, then the children can play with these kids once in a while. Okay. That's the idea. You see on the what is on the board?
Yes, teacher.
Yes, teacher.
So we have a very large person and a very small person. The only way that can effectively be done, if they are to balance each other, the smaller person must be away, further away from the pivot compared to the larger person. That's how you can at least play with that person. Is that okay?
Teacher, question.
Okay, that could be
Yes.
like 8 kilograms.
Teacher, I have a question.
Yes, please.
So what happens if the bigger person is one who's further and the small person is one who's closer to the pivot?
You will never lift that person. Even a big person, you always stay up there in the air. You can't come down until she releases you. Do you understand what I mean?
No.
Yes, teacher.
Excuse me, teacher, I have a question.
Did we do moments?
Yes.
We did moments. Okay,
Yes,
look at
teacher.
this. This question is related to moment. Look at what the blackboard, please people concentrate on the blackboard. What is the weight of the smaller person?
30 kilograms.
What is the weight of the larger person?
80 kilograms.
Okay. Then how far is the larger mass from the pivot?
1 meter.
Try 1 meter.
So we want this to balance each other. So what do we do? So what do we do? The moments are the same. Which moment is this?
What type of moment is this?
What direction?
Anti-clockwise.
Clockwise.
Clockwise moment.
Clockwise.
Okay, that's clockwise, yes. Then that direction?
Anti-clockwise.
Okay, so we want equilibrium.
I'm not going to state the other statement, anti-clockwise moment. Let's go ahead and just substitute. So I'm beginning with the anti-clockwise.
What do we do?
20 times.
20 times X. 20 times.
So we can number.
80 times 1.
Which is
So when you divide by 20
times, x is equal to
40.
4.
Sorry.
Now it is 4 meters.
4 meters. So inevitably you must be far away.
Is that clear?
Yes.
So if you are small, make sure you are far away from the pivot. Otherwise, I've told you,
yes.
Otherwise, if you have this other person can make you stay up there forever if you are not very careful. If it is a punishment, you just sit this way very far from the pivot and then you struggle coming down. If you want, that is one of the ways to disturb your stubborn brother. Yeah, you put him there, it's just like a game, then you put him forever there. But don't do that, don't bully, that is bad behavior. Is that okay? Is that okay? Okay, so the smaller person must sit further away from the pivot. So that's how you increase the efficiency. Clear? You are using a small force to lift a large force. Clear?
Yes, teacher.
Okay, that's levers. Okay, now somebody carry us through those simple notes. I've talked, I think, about levers. Simple and complicated. Let us go to that. We are talking about pulleys. Is that okay? At least we have not talked about work energy as far as levers are concerned, yet they need it. Rephrase the question. Okay, before we do pulleys, we are going to try to put down a question here, because we have to use, how do we use our different factors as far as machines are concerned? Let me put for you a very simple question, I hope. I'm talking about a crowbar, I think is the best one. Lifting a load. What is more? I don't know what I need to. This is the reason for here. And this distance is also measured from here. This will be 10 meters.
As the teacher is finishing with the paper, Lindsay, I mean with the number. Lindsay, your hand is up.
Teacher, is that 5 meters?
I just wanted to read.
Mr. Sonjole,
Yes, please.
is that 5 meters?
Yes.
Yes.
There. Okay,
Yes,
thank you,
please.
teacher. Teacher, we can't, thank you.
The diagram above shows the crowbar being used. Then the questions as follows. Work done. Okay. Yeah, it is possible.
Teacher, we can't see those last words written down there. Okay, thank you.
But distances, opposite line of action.
So the light and the angle that your laptop is placed at, we can't properly see what you're writing. So can you please adjust?
What are we supposed to do?
Is it better?
So we can't properly see everything. Like on this side, on the side where Mr. Stentovic is at.
We can.
The diagram.
Oh, you
Teacher
can.
Yes,
Suzanne
sir,
can
that's better.
see.
That's better.
Okay, first pick the diagram.
We can do it next time. Should do it because we have a levels of work done.
The units.
The units. This is going to give us even efficiencies, but in most cases, they give you a load.
Teacher, you're muted.